Hello everyone, this is Tejas Masurkar from EXTC branch of AC Patil College of Engineering, here with presenting IoT based home automation solution. This is a internship provided by Information Tech Emergy Information Technology Private Limited. In this we are going to talk about how IoT helps in home automation and home automation projects. This is our index for the project. We'll be having introduction, C programming, Arduino Unos, Pixem Lab for simulation, Internet of Things, outline of the project, and project requirement and implementation, and finally the conclusion. Let's start with the introduction. Home automation is the automatic control of electronic devices in your home. These devices are connected to the internet, which allows them to be controlled remotely. With home automation, devices can trigger one another so you don't have to control them manually via an app or a voice assistance. Like we use Blink. In this internship, we use Blink app and Arduino Uno microcontroller to control various applications such as garden light, water flow in tank, and temperature control. In this, C programming language has been used for the project completion. Let's start with C programming. It is a general purpose language. It is free formatted language. It's not strongly typed language. It is effective and portability are the important consideration. And there are numerous and hundreds of libraries present in C programming for easy user access and usability. Here are some sections of C programming. We have documentation section, pre-processing section, definition section, global declaration, main function, and user defined function. All these functions combines to form a programming code which can be then executed and implemented on. Let's talk about Arduino Uno. Arduino Uno is a microcontroller board based on the Atmega 328P. It has 14 digital pin input output pins, out of which 6 are PWM outputs, 6 analog input pins. The software used for programming this microcontroller is Arduino IDE, and it supports C programming language, which we'll be using in this project. Pixem Lab is a simulating software we'll be using. Pixem Lab is a real-time emulator of development board and integrated MP LabX AVR GDB debugger. Pixem Lab supports some Pixem microcontrollers and some SIM AVR microcontrollers. Pixem Lab have integrations with MP Lab X Arduino IDE for programming the board microcontrollers. Let's talk about the Internet of Things. The network of physical object that contains embedded technology to communicate and interact with this or their internal states or the external environment. This is basically how we can communicate with our daily fans or lights switches via a external source like a mobile phone connecting through an internet. The Internet of Things is the concept of connecting any devices to the internet and to other connected devices. The IoT is a giant network of connecting things and people, all of which connects and share data about the way they are used and about the environment around them. Here are some applications. At home, temperature control system, energy monitoring system for lights and how much consumption you have done in the month or so. Automotive, smart parking, then traffic control for better traffic during heavy hours. Agriculture, soil analysis, crop management, when to grow certain crop, which crop to grow, etc. Military, threat analysis. Medical, wearable fitness devices like smartwatches which can have heartbeats and all the other tracking sensors in it. Environmental, weather prediction, threat protection. This is our outline of the project. We'll be using Arduino Uno as our microcontroller for the process. We'll be simulating this in Pixem Lab. Here we will be having CLCD, the display for our project, and it will be connected through A5, A4 analog pins of Arduino Uno and to SCL and SD of CLCD. Then we have temperature sensors for heater, cooler, and temperature as H, C and temperature. H will be for 5 digital pin, C for 4 digital pin of Arduino Uno, and A0 for temperature, analog pin A0. Then for Ethernet shield we'll be having MISO, MOSI as 12 and 11 for digital pin, reset, and then 10 for SCS, SCLK as 13 digital pin. Then we'll be using LDR sensors. LDR sensors are for A1 and A0. Then LEDs for garden light sensing. Then we'll be using serial tank as a receiver and transmitter so that we can see how much flow of water is there in the tank. In the Blink Cloud app, we'll be giving the data streams as V1 for temperature sensor reading, then V2 for heater button, V0 for cooler button, V3 for volume, V6 for notification of the specification we are doing, then inlet valve V4, outlet valve V5. Let's start with the project requirement and implementation. So in this project we'll be doing three major things. First is the garden light control. We'll be reading the LDR sensor values. Based on the reading from LDR, vary the brightness of the LED, which resembles controlling garden lights based on the availability of sunlight. The second is temperature control system. The temperature control system consists of a heating resistor as LM35 temperature sensor and a cooler which resembles the temperature control system at home. Read this temperature from the temperature sensor LM35 and display it on the CLCD. Then control the temperature of the system by turning on and off the heater and cooler through Blink IoT app. Now for the third, water inlet and outlet valve. Read volume of water in the tank through serial communication and display it on the CLCD. Control the volume of the water in the tank by controlling its inlet and outlet valve. By sending commands through serial communication, display the volume of water in the tank on the CLCD. Let's start with the first requirement that we'll be having. The first is a garden light control. In this, we'll be using the LDR sensor to get a specific output, that is the LED, whether it is on or whether it is off. For this, let's say we have the LED is at its max, also the LDR sensor it at its max, which being its highest value, and we'll be seeing the LEDs to be glowing, but when we reduce this lower, the LED will be stopped. This is the garden light control, so that this can be implemented as a garden light, and via this we can control how much light is there or how much light is not there. Next, the second requirement for this project was temperature control system. It has multiple parts in it. The first part is sensing the temperature using the temperature sensor and displaying the temperature on a widget gauge. This is a widget gauge where we can see the amount of temperature we have. Then we have LCDs, CLCD here displaying the temperature. We have 27.34 and we have 27.34 here as well. The second requirement for this is cooler control system. Here we have a cooler button which is currently off, and we can see cooler is off and the temperature is 27.83. The input will be button, so if we turn on the cooler we'll get cooler on, and if we turn off the cooler here we'll be having turn off the cooler, so off cooler we'll see cooler is off and temperature 10, and then if the button of the is on, the cooler is on and we can see cooler is on and the temperature decreases. Now for the heater control system. Heater control system is similar to the cooler control system, where we'll be having heater as on, where the temperature starts rising. It's 32.7 now. The heater is on, and for the next one we'll be having heater is off, where the temperature starts decreasing. The heater is off and temperature has decreased. The next requirement will be threshold temperature control. In this we will be having to read the temperature. If the temperature goes above 35 degrees Celsius, the heater should turn off. So the temperature sensor will be sensing the input. The temperature is more than 35 or off, the heater will send notification to Blink IoT app and display the same on the CLCD. Here we can see the temperature has risen since heater is on. The temperature is 34.67, and as soon as it reaches 35, the heater has stopped. And this complete thing is shown on the blink IoT notification. Heater is temperature is about 35 degrees Celsius. Turn off the heater. Then the third requirement was for water tank inlet and outlet valve control. Now here we have to read the volume of water in the tank by sending commands through serial communication. This is basically the similar one for the temperature control. We have to show the water gauge and the functioning of it. So water gauge, you can see here total volume out of 3000 we have 1800 liters. It is also shown on CLCD. Water flow is on. The water flow is shown in the serial tank. For the inlet valve, the second requirement for under this underwater, if the button widget is at logic high, turn on the inlet valve by sending commands to the serial communication. Inlet valve is on, which is inlet valve is high, we start the water flow. We can see inflow on, volume is increasing and volume is present here. The second requirement for this is if the logic is low, which is your inlet valve is off, we can see inlet valve off, the water flow stops, so volume becomes 2440 and stops out. The next requirement for the outlet valve, we completed the inlet valve. Then for the outlet valve, we see the outlet valve is on, the water starts flowing outside, and we can see outlet flow on, and the volume is 2520 now. Now if the button widget is logic low, which means the outlet valve is off, the flow stopped, and we can see outlet flow off, and flow has been stopped right here. The next and the final, or not the final but the ending of this project presentation would be control the volume of water in tank. Now this is something where if the volume reaches, so our capacity was from 0 to 3000, right? So if the volume reaches from 0 to 2000, right, nothing will happen. From 0 to 3000 the volume should stop, but let's suppose we start flowing the water outside, like we open the outlet valve and now the water is flowing outside, right? So if the volume reaches till 2000, and we don't want the water to go below that, right? Because this is a requirement, we don't want water to go below 2000, so we'll start the inlet valve, and because the flow of water is same, the volume will be steady at this point. So what we do here is, if the volume reaches below 2000, we will start the inlet flow on. So we can see here the volume is steady and stopped right here. We start the flow, we reach around 2000 here, and once it reaches 2000, the inlet flow is on, and the same thing is displayed on water volume is less than 2000, turning on the inlet valve in this mobile blink IoT app. This is a final requirement where if the water tank is full, we need to turn off the water tank so that it doesn't overflow from above, and we can see 3000 and inlet flow is off, and we can show this on the CLC on the blink mobile app where water level is full, turning off the inlet valve. uh, with this I would like to conclude the presentation. In this project IoT concepts, programming simulation on softwares of different components such as LDR, LCD, I2C, temperature sensors were used and implemented thoroughly. The IoT applications and implementations were visualized. With that, I would like to conclude this presentation and on to the simulation part of this project. Thank you. So this is a simulation part of the project. Here we use LDR sensor to increase brightness of the garden light or decrease the brightness. The second part includes the mobile device. Here we turn on the cooler is on, then we turn off the cooler is off, then heater on, the heater is on, and after 35 it stops, and we get a message saying temperature is above 35 degrees Celsius, turning off heater. Then we again turn on the cooler and the temperature system is working. Next. The third part of the project starts with our water tank system, where we turn off the outlet valve and the water starts flowing. Turn off the outlet valve, the water stops. Then turning on the inlet valve, water starts, water stops. We can see that here inlet flow on, inlet flow off, then water flow on, water flow off. Now if we keep the water flow on from the outlet, we'll see after 2000 the water starts flowing again, and the notification is shown as water flow is less than 2000. And if we stop the outlet and the water starts filling to the completion, we'll see the water is full and the cooler inlet flow is off, and we can see another message saying water level is full and turning off the inlet valve.